Imagine a place in the universe where gravity is so intense that not even light can escape. A place where time and space twist in ways our minds can barely comprehend. This is a black hole, one of the most mysterious and extreme objects known to science. But what actually happens if something crosses its threshold? Will we vanish forever? Are we stretched beyond recognition? Or does something even stranger await? A secret that could change everything we know about the universe? Stay with me, because by the end of this video, you'll discover answers that are far stranger than science fiction. For decades, physicists have tried to unlock these cosmic secrets. From Stephen Hawking's groundbreaking theories to cutting-edge research at NASA and CERN, black holes continue to challenge everything we thought we knew. Before we dive in, make sure to hit that subscribe button and turn on notifications so you don't miss any of our cosmic adventures. The birth of a cosmic monster. Every black hole begins its life in violence. When a massive star, one far larger than our Sun, reaches the end of its fuel supply, nuclear fusion stops. Without fusion's outward pressure, the star can no longer resist gravity's inward pull. In an instant, the core collapses under its own weight. Temperatures rise to unimaginable levels, atoms are crushed, and electrons are forced into protons to form neutrons. The result is a cataclysmic supernova explosion. The outer layers blast into space, while the remaining core continues to implode until nothing can halt it. At that moment, a black hole is born in a region where gravity becomes so intense that escape is impossible. To an outside observer, the collapse appears frozen in time. The dying star seems to pause, hanging at the edge of invisibility as its light redshifts and fades. But to the matter within, the fall is unstoppable, a one-way journey toward an unfathomable abyss. It is here that space itself begins to curve so steeply that all paths lead inward, and time flows toward a single inevitable destination, the Singularity. The event horizon, the boundary between the known universe and the unknowable core, is called the event horizon. This invisible surface marks the point of no return. Cross it, and nothing, not even light, can ever escape. To an external observer, any object falling toward the horizon appears to slow, fading to red and never quite disappearing. Yet from the perspective of the falling object, the plunge continues normally. Time for it runs differently. Einstein's general relativity predicts this distortion of time and space. Near the event horizon, gravity's pull warps both so severely that seconds for the falling traveller could stretch into thousands of years for those watching from afar. In a sense, black holes are not just objects. They are distortions of the universe itself, places where time and space trade roles, where motion toward the centre becomes as inevitable as moving forward in time. Falling in. If you could fall toward a black hole, your experience would be nothing short of surreal. At first, you would feel the familiar tug of gravity. But as you approach the horizon, the difference in gravitational pull between your head and feet would grow enormous. Scientists call this effect spaghettification. Your body would be stretched into a thin strand of atoms as you cross the boundary. Paradoxically, you wouldn't notice anything special at the moment you pass the event horizon. There is no solid surface, no sudden barrier. The transition is silent and smooth. Only later, deep inside, would tidal forces become strong enough to tear even atomic structures apart. Beyond that, no classical physics can describe what happens. Relativity predicts infinite density, while quantum mechanics insists infinities cannot exist. Somewhere between these two extremes lies the true nature of the black hole's core. The singularity. At the centre of every black hole, according to Einstein's equations, lies the singularity, a point of infinite curvature where all matter is crushed into zero volume and infinite density. Here, time and space cease to have meaning. Every known law of physics breaks down. But most scientists believe this singularity is not a real physical point. Rather, it signals the limits of our understanding. General relativity cannot handle such extremes, and quantum mechanics has yet to provide a full answer. A unified quantum theory of gravity could reveal that the singularity is not truly infinite, but instead a region where space-time becomes quantized, granular, discrete, perhaps even looped back upon itself. Until we find that theory, the singularity remains a mystery, a symbol of human curiosity and the frontier of physics. Black holes and time. Black holes don't just warp space, they distort time itself. Close to the event horizon, time slows dramatically. This means that black holes could act as natural time machines, though only in one direction. To someone watching from a safe distance, anything falling into a black hole appears to freeze forever at the edge. Yet for the infalling traveller, time moves normally until the end. This strange asymmetry fuels some of physics' most profound paradoxes. Could information that crosses the horizon ever return? If not, what happens to the laws of quantum mechanics that demand information can never be lost? These questions lead to one of the greatest puzzles in modern science, the information paradox. The information paradox. Stephen Hawking shocked the world in the 1970s when he discovered that black holes aren't completely black. Through quantum effects near the horizon, they emit faint radiation now called Hawking radiation. Over unimaginable timescales, this radiation allows black holes to slowly lose mass and eventually evaporate. But if a black hole disappears, what happens to the information about everything that fell in? Quantum theory insists information can't vanish, yet Hawking's discovery suggested it might. Decades of debate followed. Some physicists proposed that the information escapes subtly encoded in the radiation. Others believe it remains preserved on the event horizon as holographic data. This led to the holographic principle, the idea that all the information about what's inside a black hole could be encoded on its surface, just as a two-dimensional hologram stores a three-dimensional image. As we get closer to the event horizon, things get truly bizarre. Gravity becomes so intense that it warps time and space, stretching anything that comes near into long, thin shapes. A process scientists call spaghettification. But that's not all. Some theories suggest that the information about everything that falls in might actually be stored on the surface of the black hole, like a cosmic hologram. The mysteries of black holes are far from solved, and every discovery raises even more questions. What do you think happens inside? Share your thoughts in the comments below. We want to hear your theories. The Holographic Universe. If the holographic principle is correct, it doesn't just apply to black holes, it could describe the entire cosmos. Our three-dimensional universe might be a projection of data written on a distant two-dimensional boundary, much like an image cast from film onto a screen. Black holes, in this view, are not exceptions, but proof of a universal rule, that reality itself may be fundamentally holographic. This concept, though mind-bending, resolves many paradoxes. It preserves information, unites quantum theory with relativity, and suggests that the boundaries of space hold the key to everything within. What began as an attempt to understand a cosmic monster might end with the discovery of how the universe truly works. Beyond Einstein, Einstein's theory describes how gravity shapes the universe, but it fails inside the extreme depths of a black hole. To understand what happens there, physicists are searching for a deeper theory, one that combines general relativity with quantum mechanics. Candidates like string theory and loop quantum gravity propose that space-time's not continuous, but woven from microscopic loops or vibrating strings of energy. In these models, the singularity may vanish, replaced by a finite core of immense but not infinite density. Instead of ending reality, a collapsing star could rebound or tunnel into a new region of space-time, a phenomenon some call a white hole. In such a scenario, every black hole could be the birth of another universe. Every discovery about black holes brings us closer to the edge of comprehension. They challenge not only physics, but philosophy. If space and time can end, what lies beyond? Are black holes truly destructive, or are they creative engines recycling the cosmos? When we peer into their depths through telescopes like the Event Horizon Telescope, which captured the first image of a black hole's shadow, we are looking at the boundary between reality and speculation. Beyond the horizon. Once an object crosses the event horizon, the rules of reality as we know them begin to twist into forms no human mind can easily imagine. Space and time no longer behave separately. They merge, rotate, and fold around the singularity like fabric caught in an endless whirlpool. In this realm, all directions lead inward, and motion through space becomes motion through time itself. To speak of inside and outside no longer makes sense because beyond the event horizon, there is no going back. Yet, theoretical physics dares to ask, could there be something on the other side of this cosmic veil? Einstein's equations allow for an eerie possibility that what we call a black hole might connect to another region of space-time entirely. A tunnel linking two distant points in the universe, or perhaps two different universes altogether. These theoretical passages are called wormholes, and if they exist, they could rewrite everything we think we know about travel, causality, and the limits of reality. The wormhole hypothesis. A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical tunnel carved through the fabric of space-time. Imagine bending a sheet of paper so that two distant points touch a wormhole would be the shortcut between them. In theory, one mouth of the tunnel could open inside a black hole, while the other might emerge somewhere else in the cosmos, or even in another universe entirely. But there's a problem. According to general relativity, wormholes would collapse instantly under their own gravity. To remain open, they would require negative energy or exotic matter, something that has never been observed in nature, but is theoretically possible under the laws of quantum physics. Some scientists propose that vacuum fluctuations' tiny, spontaneous bursts of energy in empty space could stabilize a wormhole for a brief moment. Others suggest that black holes could form the entry points to ancient wormholes that predate our universe itself. If even one traversable wormhole exists, it would be the ultimate cosmic shortcut, a bridge not just across distance, but across time. Time travel and paradox. If wormholes connect distant regions of space, they might also connect different points in time. A traveller entering one mouth could emerge not only light years away, but also years in the past or future. This possibility opens the door to the most profound paradoxes, imaginable altering events before they occur, meeting one's past self, or looping endlessly through causality. Physicists such as Kip Thorne have explored these ideas seriously, calculating whether nature would allow such time machines. The equations suggest that it could be mathematically consistent, but the slightest disturbance, a single photon, might cause the wormhole to collapse. Moreover, the laws of quantum mechanics might conspire to prevent paradoxes altogether through what's called the chronology protection conjecture. In other words, the universe may allow time travel in theory, but forbid it in practice. Even so, the idea lingers. Inside the black hole's shadow, time and space are no longer barriers but possibilities. White holes, the other side of darkness. If black holes swallow everything, could there exist their opposites objects that expel everything and allow nothing in? Theoretically, yes. These are white holes, time-reversed versions of black holes. In a white hole, matter and light can only move outward, never inward. In some cosmological models, a black hole in one region of the universe could be connected to a white hole in another. Matter falling into the black hole might reappear, reborn, through the white hole's mouth somewhere else, perhaps in a parallel cosmos. Some scientists have even speculated that our own universe might have begun as the white hole explosion of another collapsing universe, a cosmic cycle of death and rebirth. If that's true, every black hole could be a seed of creation, scattering new realities like stars in an infinite chain of existence. The quantum firewall. Despite the elegance of these theories, deep contradictions remain. One of the most disturbing is the firewall paradox. According to quantum theory, information cannot be destroyed, yet relativity insists that anyone crossing the horizon experiences nothing special. When these ideas collide, a terrifying picture emerges, a wall of high-energy radiation at the event horizon that burns anything entering to pure energy. If the firewall exists, the smooth, quiet crossing imagined by relativity is a lie. Instead, the boundary of a black hole would be a seething storm of quantum chaos, where information is shredded but somehow preserved in patterns of radiation. No one knows which view is correct, the gentle fall predicted by Einstein, or the fiery barrier demanded by quantum logic. The answer lies somewhere in a theory that unites both something yet undiscovered, Hawking radiation, and the end of a black hole. Black holes are not eternal. Over immense timescales, they lose energy through Hawking radiation, the slow leaking of particles from the vacuum near the event horizon. As the black hole radiates, it shrinks. The smaller it becomes, the faster it evaporates. Until one day, in the distant future, it will vanish in a final burst of light. What remains after that? Perhaps a cloud of energy, or maybe something deeper, the preserved information of everything that ever fell inside, encoded in ways we can't yet decipher. Some physicists suggest that the final stage of evaporation could reveal the true nature of quantum gravity, exposing the deepest layer of the universe's code. The black hole as a cosmic computer. Recent research has begun to treat black holes not as destroyers, but as computers' natural processors that store and manipulate information at the most fundamental level. Each bit of data that falls into a black hole might be recorded as a quantum imprint on its surface area, measured in tiny Planck-scale units. If this is true, the universe itself could operate like a vast quantum computer, with black holes serving as the processors of cosmic information. Every particle, every law, every moment could be part of an ongoing calculation, one that is constantly rewriting itself through the evolution of space-time. The simulation hypothesis and black holes. If the universe acts like a computer, could it actually be one? The simulation hypothesis suggests that our entire reality might be a computational construct, and black holes could represent the limits of that system points where the code becomes too complex to render. The singularity, then, would not be a physical infinity, but a breakdown of the simulation's framework. Though speculative, this idea offers a poetic symmetry. Perhaps we study black holes not just to understand the cosmos, but to find the boundaries of the program that created it, black holes as portals of creation. Some cosmologists propose that the universe is self-replicating. When massive stars collapse into black holes, their cores may tunnel through quantum space to form new, expanding universes. To observers inside, that expansion would look like a Big Bang. If so, every black hole might be a doorway to another reality, each new cosmos carrying subtle variations in its physical constants, an infinite family tree of universes born from the death of stars. In that view, our universe could itself be the offspring of another born from the heart of a black hole in some ancient parent cosmos. Creation and destruction, it seems, are two faces of the same eternal process, seeing the unseeable. For centuries, black holes were only equations invisible, theoretical ghosts haunting physics textbooks. Then, in 2019, the Event Horizon Telescope captured humanity's first glimpse of one, the shadow of the supermassive black hole in the galaxy M87. That orange ring of light, warped by gravity and time, confirmed decades of theory and transformed black holes from imagination into reality. Future telescopes, gravitational wave detectors, and quantum observatories promise to peel back even more layers of mystery. Soon we may not only see black holes, we may begin to decode them. Outro. Black holes continue to challenge everything we know about the universe, and while we may not have all the answers yet, exploring these cosmic mysteries brings us one step closer to understanding the unimaginable. If you enjoyed this journey inside a black hole, don't forget to hit that subscribe button and turn on notifications so you never miss our cosmic adventures. And if you want to keep exploring, check out our other videos on this channel. We have more mind-blowing space mysteries waiting for you.